Hi, welcome to another session of Circuits and Networks. In today's GATE exam, class 2 of transient analysis, we are going to see some basic problems which were asked in past GATE exams. So we'll see those problems and solutions on transient analysis. So we'll go with the first problem. It was asked in GATE 2003 for 2 marks. You can see in this figure 1. You have 4 farads of capacitor, 4 henries of inductor connected parallel with 4 ohms, and this capacitor is in series with 4 ohms. All are connected in parallel, and that is connected in series with 3 ohms, and the switch is provided, and 10 volts is going to give the energy to the circuit. So the switch is closed at time t equal to 0. We need to find out the voltage across inductance at t equal to 0 plus. So it's an initial transient analysis conditions. What we need to focus. So what we need to know is that the capacitor and the inductor behavior in initial conditions. With that, as soon as the switch is closed at t equal to 0, then what is going to happen at t equal to 0 plus? So based upon that, we have to calculate the voltage across the inductance. So the options given were 2 volts, 4 volts, minus 6 volts, and 8 volts. So we'll go with the solution. So as I told you, initially for t less than 0 means what? The switch was not closed. It was open. And therefore no energy is stored in an inductor or in a capacitor. Therefore, at t equal to 0, switch S is closed. So initially capacitor acts as short circuit and inductor as open circuit. It acts as open circuit. Now this can be understood with the help of figure 1a. Here you can see as soon as the switch is closed, the capacitor behavior is as short and the inductor behavior is as open. So based upon this condition, we need to know what exactly the value that got developed across inductance. That is the voltage value. In fact, that value of the voltage is nothing but the voltage across resistance 4 ohms. So for this, what we'll do, we'll apply KCL at node VL. So VL is the inductance voltage over here, open circuit voltage. This is known as open circuit voltage. So that voltage I am assuming here to be denoted as node VL, because these three parameters, that is the series combination of capacitor in series with resistor, is connected parallel to 4 and 4 henries. So that is why we have taken a common voltage as VL over here, and we are going to apply KCL this particular node. So from the basics of networks theory, what we have learned from our previous classes, we'll employ KCL at this node. So you have a branch current which is flowing in 10 volts in series with 3 ohms, and this 4 farad is shorted, that was connected in series with 4 ohms. So you can neglect this 4 farads over here because that is be replaced by a short wire. Then you have 4 connected parallel to this 4, and inductor is open circuited as soon as the switch is closed. Okay, so we get VL minus 10 by 3, that is the node voltage VL minus this 10 volts divided by this 3 becomes one branch current. Then you have VL by 4, that is another branch current, and you have another VL by 4, that is this branch current. So simplifying this equation, I would be getting, you can see here VL by 3, VL by 4 plus VL by 4 becomes 2 VL by 4. Uh, in fact, this becomes VL by 2. So I have taken VL outside. So 1 by 3 plus 1 by 2. And this 10 by 3 I am taking on the opposite side. Now you take a proper LCM. With this, you will get the value of VL is equal to 4 volts. In fact, from the given options, B is the right answer. I hope you understood how we have solved this problem. It's a basic concept of RLC connected in parallel as well as series combination of resistor. Let us go with another example. You can see in this example, which was asked in GATE 2005, again for 2 marks, the circuit shown in figure 2 is in steady state. Means what? The switch is open and the circuit has reached to its steady state. When the switch is closed at t equal to 0, assuming that the inductance is ideal, the current through the inductor at t equal to 0 plus equals equals what? Equals given in the option as 0 ampere, 0.5 ampere, 1 ampere, and 2 ampere. So in this figure 2, as I told you, you have to go with the basics. With the basics, initially the switch was open and inductor is reached its steady state value. Because the switch was open, the current would have flown through resistor and inductor when it reaches to its steady state conditions, it becomes short. In fact, figure 2 changes to figure 2a like this. So I of 0 minus here we are treating as the initial value of the current before the switch is closed. So the switch was open and inductor has reached its steady state value. So the current of this particular circuit, which makes the inductor as short circuit, gives the value as 1 ampere. And we should know that the property of inductor, that current through inductor cannot change abruptly. We'll employ the same principle over here. So as soon as the switch is closed, this inductor in its initial conditions of switch closing condition behaves as open circuit, but the current which was flowing through the inductor was 1 ampere. So I of 0 minus is equal to I of 0 plus, which is 1 ampere. Hence, since the current through the inductor cannot change abruptly, as I told you, the current through inductor at I of 0 plus would be equivalent to 1 ampere. So here, option C is the right answer. Okay. In this example 3, you can see there are two switches which are connected. The switches shown to be here open with the given circuit or network arrangement, and this was framed in gate 2007 for 2 marks. So let us take the data from the question, that is, in the circuit shown in figure 3, switch SW1, that is the switch, is initially closed and switch SW2 is open. So this switch was closed and this switch was open initially. Fine. The inductor L, that is this inductor, carries a current of 10 amperes, which is shown in the diagram, that is the figure, and the capacitor is charged to 10 volts as it's shown in the figure with polarities as indicated. You can see the polarities also given. Now SW2, that is switch 2, is closed at t equal to 0 minus. So this switch 2 is closed at t equal to 0 minus, and switch SW1 is open at t equal to 0. Means what? After the initial conditions, this switch was closed and this switch was open. So SW2 is closed first, SW1 is open next. The current through capacitor C and voltage across inductor L at t equal to 0 plus is, options given are 55 amperes, 4.5 volts. Option B is 5.5 amperes, 45 volts. Option C, 45 amperes, 5.5 volts. And option D, 4.5 amperes, comma, 55 volts respectively. So it's a very good question. You need to understand the basic logic of the problem. So we'll go with the basics what we have studied in our past classes, and we'll try to solve this particular GATE 2007 problem. So here, initially current through inductor is 10 amperes and voltage across capacitor is 10 volts. This is given in the problem, right? Now, what happened? SW2 is closed at t equal to 0 minus and SW1 is open at t equal to 0. Means what? This switch is closed and this switch is open. So T0 minus means before closing or before opening of switch SW1. In fact, if at all I go into the practical diagram with SW2 as closed at t equal to 0 minus, SW1 is open at t equal to 0. So you can see this figure 3 can be changed to figure 3a. So that is the important catch over here. SW1 is open, so you can avoid this switch. So that is avoided over here. That is not mentioned over here. And as soon as this switch SW2 is closed, inductor behavior initially for this condition will be open circuited, but the current through inductor was 10 amperes. And the capacitor voltage it is 10 volts. This capacitor changes to short circuit as soon as the switch SW2 is closed. So this is how figure 3 changes to figure 3a. So this is an important catch over this particular problem. Now let us assume current I flowing in 10 ohms and it is also flowing in series combination of 10 volts. If that is true, then 10 minus I is the another current which is flowing in this branch 10 ohm resistor R1. If current I is flowing through 10 ohms in this direction, the voltage would be developed in this fashion. Similarly, if current 10 minus I is flowing through 10 ohms in R1, this is how the voltage will get developed across R1. Right? Now, assuming node over here, I have applied KCL to obtain the unknown currents I and 10 minus I. Now, this is what I have framed from the given concept and assumptions. After this, I'll apply KVL to overall loop. What is my overall loop? In figure 3a, overall loop carries resistor R1, resistor R2 and 10 volts. So let us apply KVL to this overall loop. What I'll get? You can see over R1, beneath of this you have minus. So minus 10, that is the resistance. And what was the current assumed to get flowed? That is 10 minus I. So that is the current over here. Plus 10 I, which is the voltage developed across 10 ohms across R2, that is 10 I, plus 10 volts equal to 0. That's it. This makes us to give the simple solution for I. So rearranging the above equation, I would be getting 10 of 10 minus I equal to 10I plus 10. I'll remove this 10 from left hand side and right hand side. I'll get 10 minus I equal to I plus 1. With this, current through capacitor, that is I which is flowing through this 10 volts carrying of current, carrying of capacitor C would be 4.5 amperes. How is that? Because this 10 minus I equal to I plus 1. This left hand side of I goes to the right hand side, it becomes 2I. This one goes to the left hand side, it becomes 10 minus 1, that is 9. 9 divided by 2 is equal to I, therefore I equal to 4.5 amperes. This is the first step we need to concentrate. In fact, option D is the could be the right answer. Let us see whether we're going to get the 55 volts as the voltage across the inductor at t equal to 0 plus. Now what happened? At t equal to 0 plus, this was a circuit what we have framed from figure 3a. In fact, the inductor would receive the parallel voltage which is nothing but the voltage across resistance R1. The voltage across resistance R1 is nothing but 10 into 10 minus I. 10 minus I is the current flowing through this branch R1 and the resistance of R1 is 10 ohms. Therefore, voltage across inductor is equal to VL of, which is equal to 10 of 10 minus I, that is 10 of 10 minus the recently obtained the value of series current, that is the capacitor current is 4.5, that becomes the series current. So 4.5 over here. So we'll get the value of voltage as 55 volts. In fact, this is the voltage across resistor R1 connected parallel to the inductor. So it's a very good problem from basic concept point of view. This was asked in GATE 2007 again for 2 marks. Let us go with the next problem shown in figure 4, which was asked in GATE 2022 for 1 mark. The circuit shown below figure 4, the switch S is closed at t equal to 0. Fine. The magnitude of steady state voltage in volts across 6 ohms resistor in, we have to round it off to 2 decimal places. So initially the switch was open, right? So in fact 10 volts is not connected to this passive elements under this figure 4. Therefore, initially the switch was open, so I can say that the capacitor voltage is 0 volts because nothing was getting energized from the source. That's why VC of 0 minus is 0 volts. So this is the first catch. At t equal to 0 plus, the circuit is shown in figure 4a. So this is how the circuit would look like at t equal to 0 plus. So as soon as the switch is closed, capacitor will act as short circuit initially, and hence this is how the circuit would be obtained under figure 4a. But what we require to calculate the magnitude of current, magnitude of voltage across 6 ohm resistor. So the steady state conditions have to be reached. So figure 4a changes to figure 4b like this for steady state condition. So this short circuit under steady state goes to open circuit like this. In fact, for t greater than 0, the circuit which is shown in 4b, and we require to calculate steady state voltage across 6 ohms. So figure 4b can be assumed to be obtained as in figure 4c like this. Since it's open circuit, this 1 ohm becomes dummy. In fact, figure 4 change it to figure 4c like this. Right? Now, let us assume the voltage at this particular node as V and ground voltage as 0, which I connected like this. Now, applying KCL at this node V, at node V. So it becomes V minus 10, V minus 10 by 2. This is branch current over here, plus V by 3. The same voltage will be present over this particular parallel combination of 3 and 6. So V by 3 plus V by 6 equal to 0. Fine. I take V outside. So 1 by 2 plus 1 by 3 plus 1 by 6 times V equal to, you have 10 by 2, which is taken on the right side. So this becomes fine. You have to take the proper LCM. With that, you'll get the value of V, which will be equivalent to 5 volts. So the answer is 5 volts. So now we talk to two decimal places. So 5.00 again gives the value as fine. So that is the final answer for this problem. So in today's class 200 transient analysis for GATE exam, which we are treating as class 2, we have seen the problem which was asked in GATE 2022, 2007, 2003, and in fact 2005. So I hope you like this video. Please share among your friends, subscribe to this channel, and please press the bell icon for the future notifications.